Hello, this is Jack Jackson. In this video, we're going to see how to find the derivative of a quadratic function from the definition of the derivative. So I'm going to my calculus collected resources here, going to derivative algebraic formulas, quadratic functions here. So this little GeoGebra applet allows us to graph some quadratic functions. Quadratic functions are polynomial functions of the second degree of the form f of x equals ax squared plus bx plus c. I'm sure you studied these quite a bit in your pre-calculus algebra classes back in Algebra 1 and Algebra 2 and pre-calculus. And here we can see what happens if we change the value of a. Notice if a is negative, it points down. A is positive, it's going up. Here's b as well. C is going to be a vertical shift of the whole thing. So there's an example. Let's see. And we can actually type one in here. 4a squared plus 4x squared plus 3x plus 1, let's say. How about minus 1? Let's see what that does. Okay, and so we can see some things here. So there's what the function looks like. And here's what's the derivative going to look like. Just look at the shape of the graph and see if we can find some idea of what the derivative would look like. Well, let's see here. This function is first decreasing and then increasing. So that means the derivative is going to be first negative and then positive. So in other words, it's going to be down here below the x-axis, and then over here it will be above the x-axis, and it crosses the x-axis right at this local and global minimum, the vertex. Whatever the value of that is, right above that on the x-axis is where the derivative is going to cross. Secondly, notice that this function is all concave up, so that means the second derivative is positive and the first derivative is an increasing function. So the first derivative is going to be down here, it's going to increase up to cross here on the x-axis and then increase on. Let's take a look at it. Hey, look at that. It turns out to be a straight line. No matter, does that still work if I change some values here? So if I change some values here, notice if I change the value of c, vertical shift, that's not going to change the value of the derivative at all. But if I change a or b, that's going to change some things around. What if a is negative? Oh, well now that line has a negative slope because the derivative is decreasing and the original function is concave down. Interesting. And of course, if we look at the second derivative, that is the derivative of the derivative, we already know that that's going to be a constant function. Okay, so let me put some numbers here for 2 and -3. Okay, suppose we have that. We'll look at some of the patterns that we have here. If you look, this coefficient here is twice the coefficient here. This one's the same, but the powers are going down one. This one at the end doesn't really matter. It disappears altogether. And of course, we know the derivative here is just the coefficient here. It's a constant term. So let's take a look at what the derivative rule is. Well, the derivative of ax squared plus bx plus c is 2ax plus b. We're going to generalize this for other polynomials and power functions and polynomials a little bit later, but right now let's look at it for here. If we click on this, we can see the formal proof of that. Let me look at this just a little bit in a bigger view by looking at this here, and let's go through the proof. Now the proof of this has to go back to the definition of the derivative. Okay, so f prime of x is defined to be the limit as h goes to 0 of f of x plus x minus f of x. Let me say it again. F prime of x equals the limit as h goes to 0 of f of x plus h minus f of x over h. That is called the difference quotient here, and then the limit of that makes the derivative. That's the definition of the derivative. So the first thing we always have is the limit sign and the equal signs just kind of come along for the ride. We're going to line those equals up, bring that limit sign down. That's not going to change. Now we're going to just do some algebra. F of x is ax squared plus bx plus c, and f of x plus h is what we see in this parentheses. So it's parentheses minus parentheses over h, the limit as h goes to 0. That's always your second step. The second parentheses has the original formula, ax squared plus bx plus c, where a, b, and c are constants here. And then what you do for the first parentheses is you take that same formula, rewrite it, but in place of the x's, put x plus h. That's what f of x plus h means. Okay, now what do we do next? Do you see any algebra we can do here to maybe simplify this or make it a little bit different? Now notice we can't just plug in h equals 0 because we're going to get 0 divided by 0. That always happens here at the beginning when we're working with derivatives. Do you see what to do next? How about can we square this out? X plus h squared, or x plus h times x plus h. We can use the distributive property or FOIL to multiply those out. Yeah, everything else is the same, but I took this x plus h squared and made it x squared plus 2hx plus h squared. All right, what else can we do? What's the next step? Well, we could use our distributive property. We can multiply the a across here, the b across here, and the negative 1 across here. Let's see what happens when we do that. Notice again, the equals are still there, the limit's still there. The equals, it's equals and then the limit. I have some students who try to put the equal between the limit and this. No, it's the limit of this. We're applying a limit to this. It is equal to the line before. Okay, anyway, using the distributive property, this gives us ax squared plus 2ahx plus ah squared plus bx plus bh plus c minus ax squared minus bx minus c. So we've expanded out that top. Now at this point, it maybe looks like we made it more complicated than we started with, but things are going to start getting better here in just a second. In fact, the very next step, things will start looking a little better. What can we do in the next step? Well, if we combine like terms, we can do some canceling here. For example, notice that minus c cancels with this plus c. The minus bx cancels with the plus bx. And the minus ax squared cancels with the ax squared. So, in fact, everything that was in this original one ends up canceling out. So what does that leave us? Well, it leaves us the h in the denominator, it leaves us the fraction, it leaves us the equals and the limit sign. But what's left are these terms right here, from here over into here, right? Well, not the bx. It leaves this term, and this term. So 2ahx plus ah squared plus bh over h, and then take the limit as h goes to 0. Again, if we plug in h equals 0, we get 0 divided by 0. That always happens with these derivative problems. But the very next step, we can do something that's going to be helpful. Do you see what it is? What can we do to that numerator? Well, do you notice they have an h in every term? That allows us to use the distributive property to factor that common factor of h out. Now what can we do? Well, since h is not 0, it's only getting close to 0, we can cancel those h's out using the cancellation property of fractions, or the fundamental equivalence property of fractions. Allows us to cancel these h's out right here because they're factors. It has to be h times something. Well, canceling that out leaves us the limit here like this. Okay, this is really good news. Things are starting to look better. So now what can we do? We can use our limit property that says the limit of the sum is the sum of the limits. So we can take the limit of this piece, and this piece as h approaches 0, and we know that this one is a continuous function, so we can just let h be 0 right there. So finally, we can actually plug all 0 in for the h's. And of course, we can just get rid of that part, and we end up with 2ax plus b. And so that proves our derivative rule, which is right here. The derivative of ax squared plus bx plus c equals 2ax plus b. Okay, let's apply that in a specific example now. So here's an example. The derivative of 5x squared plus 6x plus 7. It's 2 times 5x, 2 times the a, and then times x to the first power. So 2 times 5x, so that's 10x. And then plus the coefficient of the x term, which is 6. And then the 7 goes away. The derivative of 7 is the derivative of the constant function is 0. Okay? Let's see if you can do one. I bet you can just write the answer down to this one. I bet you don't have to do anything fancy. Just do the whole thing in your head. It's pretty simple. Okay? What's that derivative? Well, you just take the 2 times the 7 is 14, and the x goes down to the first power. And then this one just has the coefficient of 5, and the last part doesn't matter. It goes away altogether. So 14x plus 5. So there is how we can do the derivative of a quadratic function.